So this is the first proper screencast in which I'm going to talk about some of the material in the course. Recall that there are two files for notes. One is just the printed file that you will have access to, that I'll distribute. It will be available in the examination, and there you'll see much more detail in terms of text and associated equations and figures and so on. For these screencasts, and in particular in the lectures, I'm not going to go through these notes. You can access those on your own. What I am going to do though is to use the associated Beamer file. So if I close that and open up the Beamer file, do Ctrl L, let us begin. So first slide just tells you where the course is, times, location, this term. So what are we going to do in this course? Well, we're going to look at a series of objects within plane coordinate geometry. So that includes the rather uninteresting straight line, slightly more interesting circle, and then three particular loci called parabola, ellipse and hyperbola. And the individual properties and associated problems with each of these three main shapes we'll deal with over the course of this term, but all of those line, circle, parabola, ellipse, hyperbola, plus one other object which is the single point, are all considered to be conic sections. And these are essentially the plane figures that you get when you take a cone and take a plane slice through it. Further on, this just gives you an indication of the types of material available to you, which I've already gone through. So moving on to the next slide, again a simple description of how you access the material in text form. I've already done a screencast for all of this. So, background knowledge. This is the most important thing that we need to start off in terms of the mathematics for this course. And I've got a series of results which will be either familiar to you or will become familiar to you, or material that you can actually look at. So, to begin with, we're talking about quadratic equations. We will meet quadratic equations. What you need to know is that a quadratic equation written in this form, for which a, the coefficient of x squared, is non-zero, has two roots. They're either distinct and real if b squared minus 4ac, the discriminant is greater than 0. There are equal roots if the discriminant b squared minus 4ac is equal to 0, two repeated roots, and if b squared minus 4ac is less than 0, there are no real roots. So in case 1 you have two real roots which might be coincident or distinct. In the second case you've no real roots, and in the third case you have two real identical roots. If the roots are equal and opposite, then b has to be 0. Correspondingly, if b is 0, the roots are equal and opposite. All of that information can be discovered by looking at the solution in equation 2, which is the roots of the quadratic equation 1. So in this instance you can write down an explicit formula and all of those results follow from that. In particular, when we look at the sum of the roots of a quadratic equation and the products of roots of a quadratic equation, you can show that with the coefficients on the previous page of x squared being a, x being b and the constant term c, then the sum of the roots of such a quadratic equation, if one calls them alpha and beta, the sum alpha plus beta is always minus b over a, so minus the coefficient of x divided by the coefficient of x squared, and the product of the roots is the constant term divided by the coefficient of x squared. Now these are quite useful results which you don't need to be able to show where they come from. But beyond that, we will also see examples where a cubic equation appears. So this equation here shows us a cubic with a non-zero coefficient a. In this case, if the roots of this cubic equation, for which there will always be 3, but they may not be real, they may coincide, so they may be repeated, but if the roots of the cubic equation described here are alpha, beta and gamma, then the sum of the roots, alpha plus beta plus gamma, is always minus b over a, the coefficient of x squared divided by the coefficient of a. The product of the roots, alpha times beta times gamma, is minus d divided by a, so minus the constant term divided by the coefficient of x cubed. And finally, the quantity alpha beta plus beta gamma plus gamma alpha, which is the pairwise product of each of the roots added up, is always c divided by a. So you don't need to know where those results come from in the cubic case or the quadratic case. You do need to be able to use them, and that will become apparent later on. But in particular in the exam, these results will be made available to you in the notes. One obvious fact that we will use quite a lot of, which you've known for a very long time, is Pythagoras' theorem, which tells you that in any right-angled triangle, if the length of the hypotenuse is c, which is the longest side opposite the right angle, and the other two sides are a and b, then the sum of the squares of those two sides is equal to the square of the hypotenuse. Conversely, if in a triangle the length of the longest side c squared is equal to the sum of the squares of the other two sides, then the angle opposite that longest side is always going to be a right angle. On this page we see a number of trigonometric identities, some of which you will be familiar with, some of which you will be less familiar with. Again, you need to be aware that they exist when you need to be able to use them. So in particular at the top we've got the standard trigonometric identity that cos squared alpha plus sine squared alpha is 1 for all angles alpha. The second line has the standard double angle formulae, which again you can look up when needed. The third equation has got the tan of 2 alpha as a double angle formula. And then lower down you'll see the standard addition formulae for sine of alpha plus beta, with a plus in here, and sine of alpha minus beta with a minus. Similarly with cos of alpha plus beta and cos of alpha minus beta. I don't expect you to remember them, but I do expect you to know that such formulae exist and you know where to look at them. Look for them. In the same way there's a formula for tan of alpha plus or minus beta. I've squeezed another one in here, which is tan of alpha plus pi over 2 is minus cot alpha. Cot is just cos of alpha divided by sine alpha. We only use that once. The remaining 4 on this page, which are just either the sum of two sines or the difference of two sines, the sum of two coses or the difference of two coses, also useful. These are the formulae. If you take the first one, it says that sine of alpha plus sine of beta is twice sine times cos, sine of a half the sum of the angles, cos of half the difference. So we often refer to that as sine of the semi-sum, cos of the semi-difference. There are a series of trigonometric identities that you need to be aware of. There are also a series of algebraic identities. Some of them are very obvious. The first two here you'll see are just the sum of two numbers squared, the difference of two numbers squared, and if you subtract those you get a result here which tells you that the sum all squared minus the difference all squared is 4ab. That can be deduced from these. Again, sometimes useful to use. This is just the difference of two squares. For the remaining ones we're talking about power 3. So here we've got the sum cubed, the difference cubed, and this is just the binomial expansion. And then finally, the difference between two cubes and the sum of two cubes can be factorized. Again, so long as you're aware that when you have the sum of two cubes or the difference of two cubes, you can factorize them and use these formulae. You can just look them up. So coming to the end of the background knowledge, I've talked here about some calculus that you will have seen before. It's also available in the mathematical methods module and also available in the calculus module, which you should all be doing. In particular, apart from standard differentiation that you've met before, simple polynomials, simple trigonometric functions, one result that we use quite a lot is the chain rule, and that tells you that if you've got two functions, x as a function of t and y as a function of t, which by eliminating t defines a function y in terms of x, then the chain rule tells you that dy by dx can be written as dy by dt times dt by dx by thinking of the dt's cancelling, and then the dt by dx can be written the other way up as 1 over dx dt. So in particular we'll use the result that dy by dx is dy by dt divided by dt by dx by dt quite a lot. That concludes that introduction, and now we'll move on to coordinates and distance.